Quantum, quantum physics and quantum mechanics, a beginner's manual. Quantum physics and quantum mechanics explore the world of particles at the atomic and subatomic levels, uncovering behaviors and interactions that differ from classical physics. Here's a quick guide to understanding these fascinating fields. 1. Basic concepts. Quantum, the smallest possible discrete unit of any physical property, like energy. The word quantum means how much, referring to the specific, fixed amounts in which particles behave. Wave-particle duality. Particles, such as electrons and photons, can behave like particles, localized objects, and waves, spread out phenomena, depending on how they're observed. This means they can occupy multiple positions simultaneously, a concept called superposition. Uncertainty principle. Proposed by Werner Heisenberg, this principle states that certain pairs of properties, like position and momentum, cannot both be precisely measured at the same time. The more accurately you know one, the less accurately you know the other. Entanglement. When two particles are entangled, they are connected, so the state of one particle instantly affects the state of the other, regardless of distance. This spooky action at a distance puzzled Einstein and is a key phenomenon in quantum mechanics. 2. Key equations and concepts. Schrödinger's equation describes how the quantum state of a system changes over time. It's a foundational equation for predicting particle behavior, especially in closed systems. Probability and wave functions. In quantum mechanics, particles don't have a definite location until measured. Instead, we use wave functions to calculate the probability of finding a particle in a certain place. The wave function collapses upon observation, giving a definite result. Quantum tunneling. Particles have a probability of tunneling through barriers that they seemingly lack the energy to overcome. This explains phenomena like radioactive decay and is used in technologies like the tunneling microscope. 3. Applications of quantum mechanics. Electronics and lasers. Quantum mechanics explains the workings of semiconductors and lasers, crucial to modern electronics, from smartphones to computers. Quantum computing. Leveraging superposition and entanglement, quantum computers process data in fundamentally new ways, potentially solving problems that are beyond classical computers. Medical imaging. Techniques like MRI, magnetic resonance imaging, rely on principles of quantum mechanics to visualize the inside of the body without invasive procedures. 4. Interpretations of quantum mechanics. Copenhagen interpretation. Proposed by Niels Bohr, it suggests that a particle remains in a superposition of states until measured, at which point it collapses into one state. It's one of the oldest interpretations. Many worlds interpretation suggests that all possible outcomes of quantum events actually occur in separate, parallel universes. When a quantum event happens, the universe splits into multiple versions. Pilot wave theory. Proposed by Louis de Broglie, this theory suggests that particles have determined paths, guided by a pilot wave. It offers a deterministic alternative to other interpretations. 5. Studying quantum mechanics. Mathematics. A good grasp of complex mathematics, including linear algebra, calculus, and differential equations, is essential. Key experiments. Experiments like the double-slit experiment, Bell's theorem tests, and quantum entanglement studies are foundational to understanding and testing quantum principles. In summary, quantum physics and mechanics offer insights into the behavior of particles in ways that defy common logic, impacting everything from technology to our understanding of reality. While often counterintuitive, these fields open doors to endless scientific and technological possibilities. Quantum immortality. Quantum immortality is a concept arising from the many worlds interpretation (MWI) of quantum mechanics, which suggests that every quantum event creates branching universes where each possible outcome occurs. Quantum immortality applies this idea to scenarios involving life and death, particularly those in which a person's survival is uncertain. How it works. In thought experiments, quantum immortality is often illustrated using a deadly scenario, like a Schrödinger's cat setup for a human. Imagine a device that has a 50-50 chance of killing the participant based on a quantum event. According to the MWI, in one universe, the person dies, while in another, they survive. In theory, for the person directly experiencing this, there will always be a branch where they survive, regardless of how improbable the survival outcome is. This concept leads to the speculative idea that one's consciousness might continue only in universes where they never die. Thus, from the subjective experience of the individual, they might perceive themselves as effectively immortal, since they only experience timelines where they survive every life-threatening event. Of course, quantum immortality remains purely hypothetical and is largely philosophical rather than scientific, as we have no means to verify parallel universe experiences. Philosophical implications. Quantum immortality raises profound questions. Consciousness. It suggests that consciousness might have a unique relationship with the universe, potentially selecting survival paths. Subjective reality. It posits that personal experience might diverge drastically from objective reality, as a person might experience survival in a highly improbable series of events. Fate and free will. If quantum immortality exists, it challenges our understanding of free will and destiny. In each possible universe, different choices or random outcomes could lead to wildly different experiences, including ongoing survival. While fascinating, quantum immortality is primarily a philosophical interpretation without scientific support. It pushes the boundaries of how we think about life, death, and existence within the framework of quantum mechanics, adding a thought-provoking layer to the multiverse theory.